Hello everyone. Now I'm going to solve a second problem on calculating snow load. Hopefully you already saw the first video on the calculation of snow load. So this is the second problem using National Building Code of Canada 2015. In BCC 2015 code, we'll calculate one more problem on how to calculate the snow load in a problem using NBCC code. So this is also snow load, similar to the previous problem, just a little bit different parameters. So this is problem number 2. So in this problem, what is the problem given? It's given that we need to calculate the snow load for a secondary school building located in Toronto, Etobicoke using NBCC 2015 code. And what else is given? The length of the roof of the building is given 200 meter and width is also given as 80 meter. And also the slope of the roof is 35-degree with the ground from the horizontal level is 35-degree slope. So what are the given things? Given one of the given thing is it's a secondary school building. Another one is given it's located in Toronto, Etobicoke. You need to use NBCC code, and the length of the building given 200 meter, and width is also given 80 meters. 200 meter length and 80 meter width, and slope is given, which is 35-degree. So now let's try to solve the problem. This is the problem statement. So then we need to go to that same NBCC code, and we need to calculate for Etobicoke for snow load. So for Etobicoke, Toronto, Etobicoke. So we're marking Toronto, Etobicoke in the NBCC 2015 code, and we're using snow load problems. So we need to use this 1 by 50, 1 in 50 years. This type of snow can happen in once in a 50-year time period, and we need to use this parameter SS, snow load, and also the rain load, SR. So for Etobicoke, we need to take SS value, which is 1.1, and SR, which is 0.4. And this is the equation. This is the equation. SS, we'll use this equation, and this is the importance factor table. So whichever this building category is, we need to take for the safety calculations, we need to do that. So this is for the importance factor, IS. This is the IS importance factor, and we need to take one of them depending on the category of the building. So first of all, what is the category of the building? The building is located in Toronto, Etobicoke, so you can get the parameters from there, from NBCC code. And the type of building is a secondary school building. So for a secondary school building, we can go to, for secondary school, first of all, you can write the parameters for Etobicoke from NBCC 2015, we get SS equals to what? We get SS equals to 1.1. What is the unit? Unit is kPa, kilopascal, and SR is 0.4. SS, once again, SS equals to 1.1 kPa, and SR equals to 0.4 kPa. Second one is we need to use this table for importance factor, but for that we need to know what is the category of the building. Our building category is given as a Toronto secondary school. So if we go to the table in NBCC code again, NBCC 2015, if we go to table 4.1.3.1, 4.1.3.1, if you look for secondary school building, we'll see that its importance category is high. Importance category is high. And for this importance category, now we can go to this table for 162 for high. So you're taking this value 1.15. So where our importance category is high for secondary school. Secondary school. So we'll take this value, which is 1.5. So we'll take 1.5 value. So we're going to the, so from table 4.1.6.2, which is just the table in the previous slide, we can get IS importance factor is 1.15. So what else we need? We need all these parameters. So what are we need all these parameters. We know we found out SS, IS, SS, and SR, but we still need this for coefficient values. So then we can do one at a time. For this coefficient values, nothing is given for CW and CA. Is the CW value, wind coefficient, is 1 because nothing is given. And similarly, nothing is given for shape factor. So you can assume that shape factor is a regular shape building. So the shape factor CA equals to 1. So we are assuming that it's a regular circumstance. So CW equals to 1 and shape factor is 1. So we still need to calculate CB and CS. These two things, CB and CS. Now we can go to the problem. What is given? Given is length and width is given and the slope is given. Length and width is given and slope is given. So we can do one at a time. So first we can do the slope factor. Slope factor. What is slope factor? Slope factor is CS. CS. And as you see, slope is given as 35 degree. So slope is given as 35 degree, which is more than, what is the rule? Which is more than the limit, I guess. So then we can because it's, if you check that section, the snow section, we can see the equation, and then CS value should be calculated as 70 degree minus 35 degree divided by 40 degree using this equation. So the value is 0.875 for angle 35. For slope 35 degree, this 35 is this 35, and 70 and 40 are part of the equation. So then we can get that CS equals to 0.875. So then we still need to find out CB. For CB, once again, the characteristic length is not given in this problem, but the length is given. Length and width is given in this problem, 200 meter and 80 meters. So length is 200 meters and width is 80 meters. So from length and width, we can calculate the characteristic, we need to calculate the characteristic length. So characteristic length equals to, the equation is 1.0 minus 30 by, I made a little mistake. So this is not L by C, that is CB. Eraser. So this is the equation of CB. And so this is CB equation, 1 minus 30 by L by C, LC square. That is the equation for CB. And for that, we need to calculate LC. How can I calculate LC? We are given LW and length and width is given. From there, we can calculate LC equals to 2 2w minus w square by L, which is 2 multiply width 80 minus 80 square and length is 200. So we find characteristic length as 120 meter, 128 meter. So now characteristic length is 128 meter, which is more than 70 meter, also more than 200 meter. So therefore we need to use this equation, LC equals to this equation. Since characteristic length LC is more than 70 meter and also more than 200, not more than 200 meter. Since it is more than 70 meter but less than 200 meter, I made mistake once again. So erase this and then, so it's more than 70 meter but less than 200 meter. Therefore, we need to use this equation. So therefore, we need to use CP equals to 1 minus 30 by L by LC square. So we can erase some of these things here, or I can go to next slide maybe. I can just create a new slide. So because LC, or characteristic length, is equals to 128 meter, which is less than 70 meter, but more than 70 meter but less than 200 meter. Therefore, we need to calculate CV using this equation. CV equals to 1 minus 1.0, which is 1 minus 30 by LC square. Not LC, the whole thing is square. One minus 30 by LC square. The whole thing is a square. So we can calculate CV. 1 minus 30 divided by 128, whole thing is square. So the value we get, CV equals to 0.945. CV equals to 0.945. So now we got all those parameters. If you go to the previous slide, we can see, you can change the color to find out colors. Okay. So what are the parameters we got so far? We got these values, SR and SS and SR values. We also got IS values 1.15 because of importance of building, and we got CS values, slope factor or CS. So you can calculate using this equation. We got this 0.875, and because nothing is given, we assume that it's the regular. So because of regular, CW and CA is 1, and we calculated CB using this equation, 1 minus 30 by L by C square, and 128 is used here. So if you go to the next slide, so now we have all these parameters, and we got, of course, we got the CV. So now we can write the final equation to calculate the snow load. Snow load is equals to S equal multiply importance factor SS bracket SR, then bracket finished. And there are four parameters here: CB multiply CW multiply CS multiply CA. So then importance factor is 1.15, I think 1.15, and SS is 1.1 for Etobicoke, and SR is 0.4. Now all these four parameters. CB is 0.945, CW is, we assumed 1, and I trust CA is also 1, the last one, and CS is from this equation 0.875. So then we can calculate SS snow load equals to 1.506 kPa, kilopascal. So this is on area. Kilopascal is kilonewton per meter square. So this will be uniformly distributed load over the surface of the building. So if your building is this, if this is your building, so this S value will be applicable in the whole surface, like in all over, distributed all over, uniformly distributed. S equals to 1.506 kPa. If that is a building, the whole roof surface will be uniformly distributed with S equals to this snow load value. So then we will need this calculation example for to use in your project, and then we'll put how to use this. So then so you need to input this as snow load value on the SEP 2000 model or ETAPS model as a snow load. You need to input that in the model to run the analysis of the whole building. And so we need that in the project so that you can put a snow load value in the ETAPS or SEP 2000. And you will also need in assignment 2 and also, of course, midterm and final exam. So I calculated two problems in this class on snow load calculation. So I hope you can also able to calculate the wind load calculation from this similar way using this equation, as I showed in one of the earlier slides. It's pretty similar. You need to calculate all these parameters using the wind load and calculate the values. I can show the wind load equation once again. So we need to use this table, and the other we need to definitely use this table from a structural commentary, and the other one that I showed earlier. I'm looking for the wind equation. See, yeah, this is the wind equation. Pressure equals to IW Q CE CG CP. This is the wind equation, and then we need to calculate all the three parameters C, CG, and CP, and IW is the importance factor, and Q is the value given in the NBCC code, and we need to calculate CE value, CG value, and CP value to calculate the actual pressure, wind pressure. So we need to calculate wind pressure. Just one other thing is snow is just one value, but for wind, there are total three wind values. There are total three pressure values. Using this equation, CP equals to that equation, we need to get three values. One is in the windward direction, one is in this lee side direction, and one is this direction. So we need to calculate PW, P lee side, and P roof. So we need to calculate for wind. There are three parameters. For snow, just one value. for wind, there are at least three values in the three surface. In the wind direction, this is the wind side where wind coming from, and then other opposite direction, and then the roof. And this figure also shows that there's a wind coming from leftward direction, and then there's a total three values, one in the windward direction, one is in the other opposite direction, and one is the roof. And you see this figure shows how to take the CP values. And there's another figure that I showed is a truss in the NBCC code, so you need to use that figure as well. So that's how we can calculate. And also we need to do this wind load combination thing. So we need to come back to this load combination. We'll solve maybe one or two problems of land. So we need to go to this table 4.1.3.2 for calculating the load combinations. I'm just showing what is wind, C1.4W. So W is the wind load. And what is snow? Snow is the S1.5S. You can make it pointer option, laser pointer. So you see the S is the snow load in this load combination, and W is the wind load in this load combination, and E is the earthquake, dead load plus earthquake, that's all. And in this load combination, S is the wind load, snow load, W is the wind load. And in the second one, CS.5S, this is the snow load, or it's not and, it's or 0.4 W is the wind load. And similarly, there's no snow here, there's a wind, live load or wind load. And also in this one, there's no wind, but there's a snow. There's wind in the main principal load, but in the companion, live load or snow, so S is the snow. And same as this one, there's the snow here too, for E for earthquake. So the first one is only for dead load, there's no live load, snow load, nothing else, only the dead load, like an empty building without any furniture right after the construction, nothing else, only the empty building. This is for the snow and wind. This is also snow and wind. The last one is for earthquake. And of course, as you see, this is the dominant force for wind, dead load plus wind load and companion. So summaries in this class, I showed a couple of problems. One problem is snow load calculation for a television station building in North York in Toronto. And the angles and characteristic lengths are different than the second problem. And we took the parameters from the snow load using NBCC code, and we took the importance factor from this table and used this equation to calculate snow load. And the second problem, we did a different type of building, secondary school building, and in a different location, Etobicoke instead of North York. And the length and width is given in this case, not a characteristic length. And the angle is also different, 35 degree instead of the previous one was 10 degree. So we solved the, and then we took the SS and SR values from the NBCC code, and we took the importance parameter from the next lower table, in this case secondary school 1.15, and then we calculated the values. And for just one quick thing, that is for the wind calculation, we need to use this one, hourly wind calculation, either 10 year, 1 in 10 year, or 1 in 50 year. So if it is depending on how many years you're calculating, usually I use one in 50 year to stay in the safe side. So if you are calculating the wind load, so we need to consider 0.44 for wind. And in the previous problem, when we calculated the snow for the North York, so then we need to calculate snow North York. This is the North York in this problem, and the parameters are snow parameters are these two, and this is the wind parameter. So as a practice at home, you guys can try to calculate the wind load for North York and all 1 in 50 years. So as a practice, please try to calculate the North York's wind load using this equation. using this value. You need to take 0.44. And also please try to do a practice for wind load calculation using this parameter for North Etobicoke for wind. And once again, this is an important problem. We need to use it in the project and also in assignment 2 and also in midterm and final exam probably. So please try to learn the calculation of snow load and wind load very well. Of course, seismic load too, snow load, wind load, and seismic load. Okay, thanks for this second edition. Looking forward to the third one and next one.